Assalamualaikum and hello, to everyone. We are from Group 9. Let us introduce ourselves. My name is Izati. My matrix number is 189786.
My name is Aisha Debakis Ramli. Our matrix is 189935.
Hello, my name is LAX2027. My matrix number is 189940.
Hi, my name is Zulfidin Muhammad Baim. My matrix number is 189755.
Hi, my name is Yazi Shakira Hasanuddin. My matrix number is 189877.
Hello, my name is Atika Binturisha. My matrix number is 190224.
Hi, my name is Tija Hui. Matrix number is 188707.
Hi, my name is Jamie and my matrix number is 188306.
Hi, my name is Nur Amira Hani Pinjifai Shafi'i with matrix number 189668.
Hi, my name is Nur Fatina Najah binti Misnan. My matrix number is 189508.
Okay, so today we are going to discuss about the fingerprint role of spectrophotometry in bioassays. So firstly, what is spectrophotometry? Spectrophotometry is a method to measure how much a chemical substance absorbs light by measuring the intensity of light as a beam passes through a sample solution. The basic principle is that each compound absorbs or transmits light over a certain range of wavelength. This measurement can also be used to measure the amount of a known chemical substance. So spectrophotometry is one of the most useful methods of quantitative analysis in various fields such as chemistry, physics, biochemistry itself, material and chemical engineering, and clinical applications. So basically, every chemical compound absorbs, transmits, or reflects light over a certain range of wavelength. And spectrophotometry is a measurement of how much a chemical substance absorbs or transmits, making each compound different from the other based on its absorbance. We can roughly see how spectrophotometry plays its fingerprint role in bioassays. So Aisha, could you tell us a little more about the device itself, the spectrophotometer?
Okay, sure. So the spectrophotometer, it consists of two instruments, which is the spectrometer to produce light of any color based on the wavelength, and also the photometer. The photometer is to measure the intensity of light. So the these instruments are arranged so that the spectrometer beam, so that the liquid in the cuvette can be placed between the spectrometer beam and also the photometer. So then the amount of light that passes through the tube will be measured by the photometer. Then the photometer will display a voltage signal and will usually use a galvanometer to display the voltage signal. The signal changes as the amount of light that is absorbed by the liquid change. So if the if the development of color is linked to the concentration of a substance in solution, then the concentration can be measured by determining the extent of absorption of light. So for example, hemoglobin appears red because it absorbs green and blue light rays much more effectively than red rays. So that's why it appears red. The degree of absorbance of blue or green light is proportional to the concentration of hemoglobin. So when monochromatic light is light with a specific wavelength. When this monochromatic light passes through a solution, there is usually a quantitative relationship we refer to the Beer's law between the solute concentration and the intensity of transmitted light, which is I equal to I sub 0 to the power of negative KCl. So the I is the transmitted light when colored compounds added. I sub 0 is the transmitted light while using the pure solvent, and then negative K is the constant, C is the concentration of colored compound, and L is the distance that the light traveled.
Okay.
So for me,
Now, Shazim, could you explain more about the structure of the spectrophotometer?
Alright, so basically this is the spectrophotometer here. Can you see it?
Yes.
And every part of it has its function. So this the first is sample compartment. The sample compartment is used to hold the sample solution, and we must be very careful when handling with it because even a slight fingerprint can interfere with the result. And the second is the digital readout. Digital readout will show the result of the experiment. The low absorption will show the low reading, while the high absorption of the light will show the high reading of the digital report. And the second is DV mode selector. As you know, the spectrophotometer have the two modes. The first is the IV visible spectrophotometer, and the second is IR spectrophotometer. The IV visible, it will show the light with the range of ultraviolet and visible light, while the IR spectrophotometer have the range of light of the infrared. And the fourth one is the concentration factor of the adjustment control. We can adjust the concentration of the solution that can affect the absorption of the solution. And the fifth one is the print button. We can print the result. And the sixth one is the lamp power switch to switch on the lamp source, the light source of the spectrophotometer. And this is the mirror level to adjust the mirror level or the lens level in the spectrophotometer. And the power switch, most important, to turn on the power supply of the spectrophotometer. The wavelength selection, in order to adjust the wavelength, we can just slightly adjusting the wavelength selection. And this is the switch. And the 100% T and 0 A control. When we adjust it to the 0 A control, we can calibrate the machine. But when we adjust to 100% T, we can negate any absorbance of the solution. That is basically the spectrophotometer.
Okay. So, would you like to add?
So, while Shazim has explained the external structure of this spectrophotometer, my part will be the internal structures. So, here's the diagram. Okay. Obviously, this is one of the simplest diagram because you can actually the internal structure is quite complex. So, an overview of this structure. Here we have the light source, and then to the collimator, and then to the monochromator, pass through a wavelength selector which have the little slit, and then through the sample solution in the cuvette, and lastly it will go to the detector, which then the detector will detect the light and display it in the quantity form. I mean.
Okay.
So
Okay, you're not done. Okay, carry on.
okay, so the first part is the light source. The light source, there are commonly used light source. They have two types. The first one is the halogen lamp, and the second one is the deuterium lamp. The halogen lamp is commonly used for visual light, which range from the red color to the violet color, and while the other one, deuterium light, we usually use it to detect the non-visible light such as UV rays and infrared. Okay, so the next one is the lens, the collimator lens. This function is only to focus the light from the light source, and then we will focus it to a single point into the monochromator. On the other hand, the monochromator will disperse the light. So this single light will go to the monochromator, and then it will disperse it into 7 colors, for example. So for example, red color is the longest wavelength, will be around 620 nanometers, and the shortest one will be the violet color, the range about 380 nanometers. And then we have 7 colors. So how we control how we select the certain colors to be used. We have this slit. This slit have very small and 3, so it will choose the colors that we want to use. So for example, if we want red, we can adjust it into 620 nanometers. So after that, this selected light will pass through the sample solution. For example, if we want to use hemoglobin, so if it is red, it will transmit the red color. So if hemoglobin, so if we use green color, the hemoglobin will absorb the green color. So the last part will be the detector. So it will detect the light. This detector is made up from photocell. There are two types of photocell commonly used: the photo multiplier and the silicon photoiodide. So I think that's all for my part.
Okay, thank you, Zul. Now, let's go to Iazi. What about the absorption spectrum of a molecule?
Alright, so a material's absorption spectrum is the fraction of incident radiation absorbed by the material over a range of frequencies. The absorption spectrum is primarily determined by the atomic or the molecular composition of the material. Radiation is more likely to be absorbed at frequencies that match the energy difference between two quantum mechanical states of the molecules. The absorption that occurs due to a transition between two states is referred to as an absorption line, and a spectrum is typically composed of many lines. Okay, so next, the frequencies where the absorption lines occur, as well as their relative intensities, primarily depends on the electronic and the molecular structure of the sample. The frequencies will also depend on the interactions between molecules in the sample, the crystal structure in the solids, and the environmental factors, which may be temperature or pressure or the electromagnetic field. The lines will also have a width and a shape that are primarily determined by the spectral density or the density states of the system.
Okay, thank you, Iazi. Atika, would you like to explain further?
Yes, well, absorptions of spectrum of molecule selection and transitions from a lower level to a higher level, it's involves an energy transfer from radiation field to an atoms or molecules. So when atoms or molecules absorb radiations, the upcoming energy excites the quantized structure to a higher levels, and the absorptions of spectrum of molecules actually depends on the wavelength. So there is 3 molecular absorptions processes, which each one of them is involve a quantized structure and is superimposed. Firstly is the electronic transitions, which involve ultraviolet light and visible wavelengths. And the second one is the molecular vibrations, which involve the thermal infrared wavelength. And the third one is the molecular rotation, which involves the microwave wavelengths. And electronic transitions, which is the first one is ultraviolet wavelength. When the UV photon is below the ionization energy, it will strongly absorb in producing the electron transition. But when the UV photon is above the ionization energy, it will actually create a very dangerous photoionization. And the second one is visible light wavelength. It is also absorbed by the electron transition, but it will cause heating but not ionizations like the UV. And the second one next is visible light spring as the vibration arises. And the lastly is the molecular rotations by the microwave. Due to high molecular rotational activities, the absorptions of microwave radiation will positive. That's why when we cook food by using microwave, it will solely produce light. It absorbs light to produce heat, so we can heat our food. Okay, that's all.
Okay, thank you, Atika. Now, to understand better about the fingerprint role in bioassays, the main point, Jari, what is the function of spectrophotometry in bioassays?
So I will give a further explanation regarding the functions of spectrophotometry in bioassays. So a brief explanation about it includes comparing the absorbency of a blank sample that does not contain a colored compound compared to a sample that contains a colored compound. And also, spectrophotometer measures the wavelength of a compound through its color. So by using dye or a binding substance can be added so that the color, it will undergo color change, and this can be measured using the wavelength. And besides, in biochemical experiment, a chemical or physical property is chosen so that the procedure that is used is specific, and the property can be determined in order to derive more information about the quantity, purity, and enzyme activity. And besides, this can also estimate the level of an analyte in a solution, and is ideal for simple routine determination of small quantities in materials. And in gases, we can also identify the type of gases where they are being sealed in containers. And since you all know biochemistry is highly related to medical fields, spectrophotometer plays an important role in medical fields as well. This can be seen where spectrophotometer can determine the seriousness of heart attack by taking an enzyme from the blood of a patient, and we will compare it to a standard curve. And lastly, we can also screen the selected food ingredient intended for development of functional food designed to influence the growth of gut bacteria.
Okay, thank you, Jari. Ji, would you like to add to Jari's explanation?
Yes, thanks, Kathy. Okay, so I will explain more about the function of the spectrophotometry in bioassay. So first of all, it is an important technique used in many biochemical experiments that involve DNA, RNA, and protein isolation, enzyme kinetics, and biochemical analysis. Besides, spectrophotometry can be used to identify substances without even having to actually touching them. So this is particularly useful for substances that may be dangerous and highly toxic. So if you use spectrophotometry, it is safer because we won't touch the dangerous or highly toxic substances. And next, spectrophotometry is also used to measure color compounds in the visible region of light, which is between 350 nanometer to 800 nanometer. Thus, it can be used to find more information about the substances that being studied by us. And next, spectrophotometry can be used to discern between the various pigments found in plant cells, such as chlorophyll. And it is a very helpful producer for protein purification, and it can also be used as a method to create optical assays of compounds. And lastly, for the function, spectrophotometry can be used to determine the concentration of protein in the biological fluids. Yeah, that's all.
Okay, thank you, Ji. Now, we know that the spectrophotometer is a device that must be handled with care. Amira, what are the ways of handling it?
Each one of you have explained the complicated things, the principle, the structure, and whatnot about the spectrophotometry. So I would like to explain what the basic things, the ways, and the guidelines of handling the spectrophotometer itself. So as you all said that the spectrophotometer is an experimental technique that
solution by calculating the amount of light absorbed by the solids. So this is a powerful technique because certain compound will absorb different wavelength at different intensities. So every steps must be done particularly so the machine will interpret an accurate reading. So first of all, turn on the spectrophotometer and let it sit or in other words warm up for 15 minutes for it to function and give an accurate reading. So while waiting for the machine to warm up, so make use of the time and prepare the samples itself. So secondly, make sure to use clean cuvettes and test tubes. Since we're dealing with reusable cuvettes or test tubes, make sure they are properly cleaned with deionized water. This is because dirty cuvettes or test tubes will affect the light absorbed by the liquid itself. So less light will reach the sample, so the machine will interpret the result as more light is absorbed by the sample. And as I said before, it must be clean with deionized water. Deionized water is a water with no impurity ions. And in fact, it is a perfectly clear water and its purity degree is much higher than the distilled water. And since we're dealing with cuvettes, which is quite expensive, so handle them with care. Besides that, since the cuvettes and test tube have different maximum volume, so load the proper value of each sample into the cuvette. For example, the cuvette has a maximum volume of 1 milliliter and test tube have the maximum volume of 5 milliliter. So load the sample according to maximum volume of each cuvette and test tubes. As long as the light producing laser pass through the liquid and not the empty part of the container, the machine will interpret the result and give the result accurately. And about the cuvettes, make sure the cuvettes are clean. In other words, wipe the outside container of the cuvettes and avoid touching the sides of the cuvette since you want to avoid interference with dust, particles, and whatnot. And maybe you can use a lint-free cloth to remove the water droplets or fingerprints itself, so that the outside of the container of the cuvettes is clean. So that's all.
Okay, thank you, Amira. Now that everyone has explained the main points, so for a clearer picture, Najah, could you tell us how hemoglobin is measured by spectrophotometer?
Okay, since we all already knew that the visible white spectrum is made up different wavelengths, so each representing a particular color, the machine operates by passing a beam of light through a sample and measures the amount of light that is absorbed by the analytic or product of the analyte. So, how does spectrophotometer measure hemoglobin? In order to count leukocyte and measure the hemoglobin, a lysing agent was added to the sample of the diluted blood. The lysing agent simultaneously lyses the red blood cell and keeping the leukocyte intact and releasing the hemoglobin. The lysing agent contains potassium cyanide that reacts with and converts the hemoglobin to a stable pigment, which is the colored product called cyanomethemoglobin. A spectrophotometer with wavelength set at the peak absorbance of the cyanomethemoglobin measures the concentration of hemoglobin. The absorption of the cyanomethemoglobin is directly proportional to the hemoglobin concentration of the sample. So is it clear?
Yes.
Okay, that's all from me.
Okay. So in conclusion, now we know how spectrophotometry plays its fingerprint role in bioassays, which is by different chemical substances absorb different wavelength of light at different intensities. It functions almost as an ID for each chemical substance.